The interdependence between human health and planetary health has never been more clear. As we start a new decade, it is time to focus on the future we wish to build, and indeed leave for generations to come. Humanity has made incredible progress over the past century, yet the cost of this progress has caused immense destruction to the planet that sustains us. We simply cannot maintain this course indefinitely. To build a productive and sustainable future, it is critical that we accelerate and mainstream sustainability into every aspect of our economy.
The planet is warming. Now there is no room for doubt that the climate is changing and human activity is to blame. The main reason is the increase of carbon dioxide and other greenhouse gases that trap the radiation from the sun. Most of this is due to the use of fossil fuels. Carbon trapped deep in the earth for millions of years as coal, oil or gas, burned for energy and releasing carbon dioxide. The world's fleet of commercial aircraft burn kerosene derived from oil. Estimates vary, but they probably contribute approximately 2 to 3% of global carbon dioxide emissions. As the urgency of the problem of climate change increases, the world's aircraft manufacturers know that the commercial aviation sector must mitigate this contribution in the next few years and ultimately eliminate it altogether. Governments are waking up to the unfolding emergency. The United Nations is attempting to coordinate the global response in a series of climate change conferences. More specifically, there are changes affecting the airline industry. Some Scandinavian countries have set ambitious targets for aviation. Most notably, Denmark has set a target for 100% fossil-free fuel for domestic flights by 2030. In 2022, EasyJet unveiled its roadmap to net zero, a plan based on emerging technologies in aircraft design and propulsion. This plan aims to bring its aircraft operation to net zero carbon emissions by 2050. In the UK, the government has created Jet Zero Council, a partnership between government and industry with the declared aim to deliver zero-emission transatlantic flight by 2050. How realistic are these ambitious targets? Does the technology exist to fulfill these dreams? In this program, we will look at the research and trials and talk to the people striving to deliver a sustainable airline industry. In addition to the big players like Airbus and Boeing, the need for the aviation sector to decarbonize has spawned hundreds of small companies and startups around the world with innovative ideas for green aviation.
Hi, my name is Neil Cluffley. I'm the CEO and founder of Faraday Aerospace. We're one of the new generation of sustainable aircraft manufacturing companies based here at Duxford in Cambridgeshire. So why are we here? Well, basically I spent many years in commercial aviation, selling, owning, leasing, managing aircraft in commercial aerospace with airlines, banks, etc. And aviation has always done very well at advancing and becoming better technology, cleaner and greener. So if you remember back to the 1970s, we're looking at situations where you had plumes of black smoke out of the commercial aircraft. Don't see that today. So as an industry it's doing very well, but as we increase flying more, there is of course more that we can do, and that's the reason why we're here. We're basically looking at bringing new technologies to aviation to allow us to fly cleaner and greener, and basically allow you to fly as well.
So, why are Cranfield Aerospace doing what we're doing? Well, first of all, a little bit of history about Cranfield Aerospace and where we come from. So, we've been around for about 30 years, and during that time we've been doing a whole load of really interesting engineering development projects for the likes of Airbus, Boeing, Rolls-Royce, all those big aerospace companies that everyone knows. And we have been essentially designing and certifying complex modifications to aircraft for about 30 years. We also still continue to do the continued airworthiness for the Battle of Britain Memorial Flight Spitfire and Hurricane fleet, and we're very proud of that and we'll continue to do so. But about 5 years ago we decided to change our strategy from doing work for other people to help change the world, and we decided to do that by using our capabilities and our approvals to convert an existing aircraft to zero emissions propulsion and to bring that product to market by 2026.
One obvious way to make aircraft zero carbon emitters would be to power them by electricity derived from renewable generation. The idea of electric planes is nothing new. Experimental electrical aircraft have been around for about 50 years. The first recorded electric plane that could take a passenger was in 1973. The aircraft was a modified motorglider called a Militki MBE-1. It could fly for 12 minutes powered by a nickel-cadmium battery. A more recent spectacular achievement was by the Solar 2, an electric plane powered only by the sun. The solar panels were placed on the massive wings. The Solar 2 had a wingspan similar to the Airbus 380, which is the world's largest passenger airplane. In 2015, the Solar 2 flew round the world, over 42,000 kilometers at an average speed of 76 kilometers per hour. The journey took over 6 months in 17 stages and was fueled totally from solar power. With the recent advance of the climate agenda, electric cars powered by lithium-ion batteries have suddenly entered into the marketplace with some speed. Initially powered by Elon Musk's vision and his Tesla brand, it now seems that every few weeks another major car manufacturer is announcing a launch of their new all-electric fleet, with the result that prices are falling. These all-electric cars are becoming serious contenders in this crowded marketplace. There has been much progress in adapting this technology to aviation. In October 2022, a fully electric passenger plane built by an Israeli company, Eviation, took off from Grant County International Airport in Washington State and flew at 3,500 feet for 8 minutes. The flight was a proof of concept of a commercially viable all-electric plane. The plane, named Alice, is designed to fly up to 650 miles at 10,000 feet with a cruising speed of 276 miles per hour on a single charge, and the battery can be fully recharged in 2 to 3 hours. There are now several companies across the world competing to bring battery-powered electric planes to the short-haul sector. One example is Heart Aerospace, a company based in Gothenburg, Sweden. They are developing the ES-30, a battery-powered electric plane designed to carry up to 30 passengers up to 200 kilometers. The plane carries reserve hybrid turbogenerators which can also be used to extend its range. The company hopes to bring this airplane into commercial service before the end of the decade. Another company, Seattle-based Magnix, have taken a different approach. They have designed the electric motor that powers Alice. These motors are designed to be easily installed in existing small planes to replace the conventional engine. This would allow operators like Vancouver-based Harbour Air, which is Canada's largest seaplane operator, to refit their entire fleet instead of having to replace all the aircraft. When it comes to attempts to scale up this technology in the aviation sector, however, there is a major stumbling block: the weight. Omar Bey Yohei, the CEO of Eviation, has described the all-electric plane, Alice, as a huge battery with some plane painted on. Batteries that store the amounts of energy required to fly are heavy, extremely heavy. This is a minor problem with automobiles where energy is required for forward propulsion only, but a major problem for aviation where most of the energy is required to maintain lift.
First of all, we looked at batteries because there was a natural zero emissions solution. It works in cars. So we had a look at batteries, but actually it didn't take us very long of doing calculations to figure out that actually, because of the really low energy density of batteries, they have a tenth of the energy of kerosene in the same weight of fuel. That was never going to work for aerospace. Nothing but the smallest aircraft will benefit from the use of batteries because they just can't get enough juice out of them. So a conversion of a Britain or an Islander using batteries alone would get about 20 minutes of flight, and that's just not enough for credible operations. So we looked at hybrid electric, which is a conventional engine with batteries, because then you get the range. But unfortunately, because of all the redundancy that you need for safety, it means you're having two batteries, two engines, and you end up carrying so much weight around with you that actually your reduction in carbon emissions, if you get any, are no better than just developing a more efficient engine. And we didn't really see the point in putting a lot of money into that.
The difference lies in the way that batteries and jet fuel store energy. Batteries store energy electrically, but jet fuel stores energy as chemical bonds between the atoms that make up the fuel. During its combustion, these bonds are broken, releasing massive amounts of energy stored in them. This difference means that a kilogram of jet fuel stores more than 80 times the energy that can be stored in a kilogram of lithium-ion battery. It is this difference in energy holding density that means that the use of battery-powered electric plane is going to be limited. The search for new battery technology has been frustratingly slow. The most promising studies are into lithium-sulfur and metal air batteries, which use the air as one of the terminals. In theory, a lithium air battery could achieve near the energy density of jet fuel, but progress is frustratingly slow. There has been a working prototype of an aluminium air battery, but it is not rechargeable as the aluminium component is destroyed during discharge. However, with the potential rewards awaiting, huge amounts of research are being conducted in this area. One way to deal with this problem is to revive an old technology, the airship. This uses the natural buoyancy of a lighter-than-air gas, like heated air or helium, to create the lift without having to use the aircraft's power, so the battery weight becomes irrelevant. Hybrid airships, however, have limitations. They are slow traveling at about the same speed as normal road traffic. Crossing the Atlantic would take days. They are also much more weather dependent and very expensive to build and maintain. They are most likely to find a use in shipping cargo.
Airlander is the world's most efficient large aircraft. It's designed to deliver 10 tons of freight, 100 passengers, and to deliver them to places, or take them to places, at only 10% the emissions of other aircraft. we do with Airlander is combine some of those technologies that were in airships of the past, but we put that together with a lifting wing. We use modern materials and modern technologies to give us an aeroplane that's super efficient, but still takes off and lands from the ground like other aeroplanes. Different to airships, which of course float. The experience is totally different for a passenger. We think of Airlander as much as a fast ferry, because it's big, it's spacious, every seat is accessible to the aisle, you can move around. Big windows, flying much lower, it's very gentle, so none of that vibration and turbulence that we're used to in other aircraft.
The inherent weight problems with battery-powered aircraft has led other researchers to look into alternative ways of powering electric planes. Electric planes are eminently suitable for the short-haul industry, journeys limited to about 250 miles and a small number of passengers. They will be effectively Airbuses or Airvans for freight. However, since nearly half of global flights are less than 500 miles and 80% of commercial flights are short-haul, less than 3 hours of flying time, these electric planes could make a huge contribution to a reduction in the carbon emissions of the world aviation industry. This is the sector of commercial aviation that is likely to see the most significant reduction in carbon footprint in the next few years. In large countries like the United States, domestic flights are an integral and important part of their transport infrastructure. Faradair, based at the historic Duxford Airfield, is looking to use an electrical generator powered by sustainable aircraft fuel.
There are new technologies, electric motors. We've seen cars, 2.5 tons of machinery accelerating faster than supercars. If you'd said that a four-door saloon would out-accelerate a Lamborghini 10 years ago, you probably would have been laughed out the room. It's a common occurrence now. Everybody can do it. But the great thing is that technology, that single motor, single piece in that electric motor with no other moving parts is a real great piece of technology innovation. It means that we can use it for a long period of time without having to maintain it, without having to repair it. That's fabulous. But whilst electric motors are fantastic and they give us this great opportunity, the big question comes with how do you power it? That's the core crux. We've seen with battery technology today that's quite limited. It's quite heavy. It doesn't quite have the power density that we need at the moment, but it is getting better. But it also has some nasty habits as well. There's occasion of thermal management where it does like to have a party on its own sometimes and create a fire. So you have to manage that process as well. So these technologies will improve. Likewise, hydrogen fuel cells, ammonia fuel cells. All of these new clean technologies are currently being worked on and they will be implemented. Of that there is no doubt. The question is over what time frame. With our aircraft, we decided that we would try and use that same principle that has allowed the 787 and the A350 to do the routes that the A380 and the 747 big airliners used to do with just 2 engines. We want to do the same with regional flight, where we take 2 turboprop engines and instead we use just 1 turbine, effectively a box of power if you like. It's a power source. In that we'll use jet fuel. But over time, we're going to put more and more sustainable aviation fuel. It's called SAF. That gets blended in to a point that when we're eventually using 100% SAF, we're almost at a net zero point with our aircraft. But that's a here and now solution. It's a solution that will last us up to the next 10 years. As the other technologies mature, what we'll be able to do with this aircraft, which is a short takeoff and landing, all carbon composite aeroplane, is take that box of power out, put a different box of power in the future, and we truly do have a net zero aircraft. So this is the first step on the ladder, if you like, to our sustainable aviation future.
Small companies and startups are often more innovative in their approaches. Small numbers of people can usually make quick decisions rather than endure the inertia inherent in a large organization. They tend not to be restricted by heavy investment in current technologies and practices, and are free to think more radically and develop bolder ideas.
So with our aircraft, the Bihar, a lot of people look at it and they say, wow, it's got 3 wings. Is that the Red Baron's plane? In fact, I was on a US breakfast show talking about the old Fokker triplane. The amazing thing was the triplane was actually created by Thomas Sopwith. It was a British invention first, which the Germans then evolutionized into a very efficient aeroplane, to the point that if you went up against a Fokker triplane in World War I, you were in real trouble. It was a very effective aircraft. So when we first brought this project to the fore, a lot of people are like, 3 wings, oh, very draggy, why do you want to do that, and all the reasons that they put forward. It's 100 years ago we gave up all of that. But actually, when they did the studies, when it was actually tested and looked at against 6 different wing configurations that were proposed by others to look at as a comparison, this wing configuration came out the best. But you will always get the naysayer. It is something that we will always battle because everybody has an opinion, but not necessarily everybody has all the facts that back up the information of why you're going down a path.
Modern computer technology also means that novel ideas can be tested much more quickly.
What we've seen through history is the fact that technology now offers us an amazing opportunity to do things in a much shorter time frame. Imagine what a Formula One team goes to a race one weekend and they see something appear on a car. They think, wow, into the computer, into the engineer's hands. Within 2-3 weeks later, they have something similar on their system. In the days gone by, we used to have aircraft designed by models and clay and wind tunnels, and it would take years. Now, with the power of computers, we can do things in a week that would have taken us 18 months to do in the past. What does that mean? Well, it means that we can look at different designs. It means we can look at different options. Do we have to have that wing and tube shape? Could we be flying a blended wing across the Atlantic? This big, great big flying wing. Could we be flying something that's much faster? The shape is much more fuel efficient. Who knows? But computers and processing power allows us to look at all these options much quicker now.
Neil's vision for the short-haul sector goes beyond his new airplane. He believes it could bring in a new regional air transport network which could radically alter the way we travel.
Yourself is, where am I going to fly this aeroplane? What's it going to do? Well, of course, we're not going to have you go across the Atlantic on an aircraft that flies at about 200, 250 knots. It's designed for the movement of people, boxes, cargo, equipment. So therefore, it's effectively the flying van. What it means is that you've got intercity regional connectivity. At the moment, it's being given the phrase, we started talking about regional air transport back in 2014 when we formed the company. Today, that's evolved. There are studies now from the likes of McKinsey, NASA, various bodies talking about regional air mobility. Now, regional air mobility is basically the ability for you to fly between cities like you would be taking a bus. And that's what we're trying to do. We're trying to bring you that environment where you can see your regional airfields as a valid part of your transportation options. Now, if you look at land transport today, you're tied to the train, you're tied to the car, you're tied to a coach. We're here at Duxford in Cambridgeshire. A lot of our R&D for our aircraft is being done in Swansea in Wales. Anybody that's done a journey from Cambridgeshire to that far west in Wales know that that is a 5 to 6 hour journey process. Wouldn't it be great if we could do that a lot quicker via an aircraft that was affordable, that you can just use like you would an ordinary part of your daily transport? That is what we're doing here with the Bihar.
Small zero-emissions aircraft coming into service is far more than that technology step required to scale up the rest of the industry. It's in itself a huge market opportunity and actually a way of redefining regional connectivity. So back when these aircraft were first invented and first came to market in the sort of 60s, the demand for sub-regional transport was huge. Over the years, however, that sector of the market has been significantly underinvested in, and the reason for that is because of the economics of kerosene. It's quite difficult to make small aircraft operations profitable. So as larger airframes came on board, airlines tended to move from the really short hops to the longer journeys and the larger aircraft, because then the cost per seat, per passenger, goes down and you can make more profit. So the whole theme of this industry has been to go from ever larger aircraft until it culminated in the A380, and then everyone realised, well, we got a bit too far there and started coming back down again. But that's essentially what's happened, which means the sub-regional markets, these 9 to 19 seat aircraft, have not had any investment in them for some time because of the economics of kerosene. You bring zero emissions and hydrogen technology into the market, which has lower operating costs of up to 50%, lower fuel costs, because even though hydrogen may be slightly more expensive than kerosene, you only need a third of the fuel. So you start creating an economic viability now for these sub-regional journeys. Sub-regional journeys, by the way, the demand has not decreased. The demand is still there. In fact, it's probably increased because you have so many more people.
Cranfield Aerospace are taking a different approach. They are also looking at an electric plane, but powered by a hydrogen fuel cell.
So the first question people ask is, why consider hydrogen as a fuel for aviation or as an energy storage means for aviation? Well, fundamentally for hydrogen offers us potential for zero emissions aviation, potentially as zero CO2 emissions at the tailpipe, at the exhaust of the power unit of the aircraft, but also depending on how the hydrogen is created and then transported to the aircraft, potentially a completely zero emissions energy solution for aviation. So in terms of how does a hydrogen fuel cell work, or how does a hydrogen propulsion work? Well, effectively, if you consider our energy is stored as hydrogen in gaseous form on underwing tanks in our aircraft and its product configuration. And we need to convert that gaseous hydrogen and the potential stored chemical energy in that hydrogen into propulsive energy for the aeroplane. So we take the gaseous hydrogen from our fuel tanks and feed that gaseous hydrogen into our hydrogen fuel cells themselves. And the hydrogen fuel cells are where the electrochemical process takes place to take that hydrogen in, plus the oxygen in the atmosphere, we take that in as well, and they combine in an electrical chemical process to create energy, electrical energy, waste heat, and our own exhaust, which is effectively water vapour. We take the electrical energy that's output by the hydrogen fuel cell itself, and we pass that through, we use that as motive power to drive an electric propulsion unit or electric motor, and we have an advanced electric motor for Project Fresson. And that electric motor is very compact, very high efficiency, and that drives our conventional propeller to provide thrust for the aeroplane.
Because of the urgency of the climate emergency, Cranfield is planning to fit their new system into existing proven and certified airframes. This should enable these aircraft to be certified for commercial flight much faster than designing a completely novel airplane.
So what are we doing? We are converting a little aircraft called the Britten-Norman Islander. Now this is an aircraft that's actually built in the UK. It's the last remaining whole aircraft to be built in the UK, and it's an absolutely cracking little aircraft. The reason why we chose it is because it's small, which is where the technology is at the moment, and also because although it can actually fly 1,200 kilometres, the vast majority of its operations are actually short hops. So in the UK, for example, you'll find them flying around in Orkney and also between Land's End and Scilly Isles. And it's those sorts of operations that the Islander is really good at. It can land on grass, ice, beach, anything that looks remotely like a runway, your Islander can land there. It's an aircraft that's loved around the world, and it's very robust. It's also quite a simple aircraft, and so to modify it is easier than modifying something that's more complicated. So we chose the Islander to put in our hydrogen propulsion system.
The Islander has two conventional engines, one on each wing in the engine pods or nacelles, and with our system, in each nacelle we remove the conventional piston engine completely. That's no longer part of the system, and in each nacelle we fit the hydrogen fuel cell system, which is the combination of fuel cell stacks and their balance of plant, so the power station. So we fit the hydrogen fuel cell system in the nacelle, and the hydrogen fuel cell system provides the high voltage, high power output to drive the electric propulsion unit, which is also in the nacelle, which is electric motor to drive the conventional propeller. So we replace the piston engine with the fuel cell system and the motor in the nacelle. Mounted below the nacelle will be the thermal management system, so the heat exchangers that deal with that high heat, low temperature waste heat from the hydrogen fuel cell system itself, so that's part of the nacelle as well. And then in terms of the fuel store, the fuel tanks, they're external underwing tanks shown here on this rendering, so that's where we store the hydrogen fuel in gaseous form.
For Cranfield Aerospace, this is just the start of a journey.
Hydrogen fuel cells is very much a scalable technology. People are already looking at increasing from, I mentioned, the 250 kilowatts each side we've got into something of the 1 megawatt, 1.2 megawatt class, and then you can multiply those across the aircraft. So it's a very, very scalable technology, all the way up to potentially large commuter aircraft, large regional aeroplanes of the 50 to 100 seat class.
The small retrofit of a small aircraft is phase one, but we want to scale up and we want to be able to try and help decarbonise the rest of aviation, because these little aircraft are not in themselves going to decarbonise aviation, but what they will do will facilitate possibly one of the greatest revolutions in transportation history by getting those first challenges knocked down, by figuring out how to certify hydrogen in aerospace, by helping airports understand how they can handle hydrogen as an aviation fuel. The regulatory authorities need to figure out what certification rules and regulations need to be written for hydrogen, because everything is written about kerosene right now, and when you introduce hydrogen into the mix, everything changes. So all of those things need to be put in place, and these small aircraft help that to be done more quickly. They help it to be done this decade instead of waiting till 2035 when the large ones start arriving. So this is phase one. It's there to prove the technology, to prove all of the infrastructure and the ecosystem around it. But our phase two then goes on to a larger aircraft, probably moving from gaseous hydrogen to liquid hydrogen at this stage. So there are two ways of storing hydrogen in an aircraft. One is to pressurise it in really heavy tanks, which is what we're doing on the first phase, and that's in gaseous form. The other type of storage is liquid storage. So liquid hydrogen takes up 4 times the volume of kerosene, but it has 3 times the energy contained within it. But to keep it in a liquid state, you need to cryogenically cool it to minus 253 degrees. So high pressure and heavy, or not as heavy, but cryogenically cooled. Both have their challenges, but we only really need liquid hydrogen when you want to get that extra range, and that once you start getting into aircraft of probably about 15 seats and above, you start needing to need that liquid hydrogen, because otherwise the gaseous tanks are just starting to get too heavy from the amount of fuel you need to carry. So phase two is getting into a conversion of another aircraft and going liquid at that stage to get more range and more people in. Phase three is where we really start to live our dream, because our ambition is to be a designer and manufacturer of clean sheet, zero and low carbon emissions aircraft. So phase three is about our new aircraft that will be designed around the hydrogen propulsion system. Because the thing with hydrogen propulsion is, it's not like an engine you can just stick on a wing. It is really quite integrated into the airframe design, and it has quite a lot of implications for airframe design. So for example, in your normal aircraft these days, kerosene is actually kept inside the wings. But when you're cryogenically cooling the fuel, you can't really do that. So you can't put liquid hydrogen in the wings of an aircraft. So it would need to go either in the fuselage or in an underbelly or over fuselage pod, which obviously that in itself has an impact on that airframe design. But then you've also got wings that aren't heavy with fuel, so they can be designed differently, well, they have to be designed differently, but they can also be designed in a more efficient way to help with the aircraft performance. So hydrogen propulsion essentially has a massive impact on airframe design. So in order for it to be as efficient as possible, and let's face it, we all need to focus on using as little fuel as possible, not just new fuel. In order for it to be as efficient as possible, you need to be having the airframe and the propulsion system working together to create that optimised aircraft, which is what we want to do in phase three. And that would be an aircraft between 20 and 50 seats, depending on what the market needs. The final phase, which we'll get to probably when I'm retired, is a larger regional aircraft of up to about 100 seats, using the same sort of technology.
There are many other projects developing along similar lines all over the world. One of the major hurdles to this type of research and development is getting the funding. This is big engineering, and the equipment does not come cheap.
So Faradair has been going for 8 years now. If somebody had taken me to one side at the beginning of this journey and said, this is what you're going to face being a startup, this is what your life is going to be like, I can tell you now, you would give it second reservation, you would give it second thought. It is hard, it is really hard, and that is the story of every startup company. What you're trying to do is you're trying to push boundaries, you're trying to push innovation, you're trying to pioneer new things. There's a certain amount of risk in that. Now the problem with that is somebody has to pay. Now if you look at America, there is a culture where there's 20 reasons why you can do something and 5 people prepared to fund the operation to do it. Here in the UK, you'll find that there are sometimes 20 reasons why you can't do something, and other people will come up with reasons why you shouldn't be doing it. Well, we've had to fight through that, as have many companies. There's people like Rivian who've moved to America. We ourselves almost moved to America in 2019 because the funding system that we have here in the UK is very risk averse. We can go through a system of choice, which is if I make no decision, it can't be the wrong decision. We can give money to a huge major corporation because it's industry, so how can that be wrong? That must be safe. Or we can give money to these small companies, these SMEs, these innovators, these pioneers. But there's more risk to that. Do I want that risk associated with me, which ends up pushing us back into option 1 and 2, which is do nothing or give money to big corporations? And I think we have to be bolder. The Americans have a great phrase, which we don't quite have for, if you're playing cricket, it's hitting a 6. But the Americans say swinging for the fences. That's a baseball term. You get 3 strikes, you hit the ball and hit it over the fence, it's a home run. What we're trying to do here in aerospace now is have lots of home runs by developing innovation quickly. The best way to do that is with small teams, innovative teams, low-cost teams. That is what we're trying to do, and of course, that is something that the UK has always struggled with. Even in the times of Sir Frank Whittle, Barnes Wallis, R.J. Mitchell, even himself with the Spitfire in 1934, could not get an ear to listen to the design he had to what was one of the most iconic aircraft of the Second World War. So that is the world that we operate in, and you do it as best as you can, so we grind forward. But to date, we've not been able to have any taxpayers grant funding. It's disappointing because we have won pitching events around the world, we've spoken at conferences around the world, we've represented the UK globally, and I think that we really do need to start supporting our smaller companies an awful lot better. If we do, we can lead the world. You only have to look around Duxford, go into air and space, look at all the incredible aircraft we have created over our time period. The UK is one of the very best at coming up with innovative aerospace technology. What we've got to do better is backing those pioneers and innovators to help us still maintain our position in the world as one of the best in this business.
All these electric planes, whether powered by fuel cells or batteries, rely on propellers to deliver thrust. When it comes to looking at the long-haul intercontinental routes, however, these aircraft are unlikely to be able to replace modern jetliners like the Airbus or Boeing Dreamliner. Firstly, they are slower, typically traveling at speeds of 250 to 400 miles per hour. The Dreamliner travels twice as fast close to the speed of sound. Propeller-driven aircraft can also not fly as high. As altitude increases, the air becomes thinner, which reduces the thrust that props can generate. These aircraft typically fly at about 25,000 feet. Jets will typically fly at 35,000 to 40,000 feet. At these altitudes, air is only 20% of its density at sea level, and a propeller cannot deliver enough thrust. A jet engine has no such problem. The reduced air density means that there is much less drag on the plane, and so it uses fuel much more efficiently. It is unlikely that the jet engine can be replaced for the long-haul sector in the foreseeable future. In the next program, we will be looking at how the long-haul sector can get towards zero emissions by using sustainable aircraft fuel, increasing the efficiency of the engines, and eventually moving to the ultimate goal of using hydrogen to power a new generation of jet engines.
fast running out, and we are rapidly wiping out through mass extinctions many of nature's unique treasure trove of species from which we can develop innovative and sustainable products for the future. Timelines for change must be brought forward if we are to make a transformative shift by the end of the decade and before it is, quite literally, too late.